Picture this. It's 1950, the Korean Peninsula is erupting in warfare, and American tank crews are discovering their supposedly superior M4 Shermans are being picked off like sitting ducks by Soviet T-34s. The problem? They can hear American tanks coming from over a mile away. The roaring gasoline engines, the grinding transmissions, the mechanical symphony that announced, "Here we come," to every enemy position. Meanwhile, Soviet tanks could creep up almost silently, their diesel engines purring at frequencies that blended into the battlefield. But buried in Detroit, in a factory that made city buses, sat an engine that would flip this entire equation. An engine so unlikely, so overlooked, that even the military brass initially laughed at the suggestion. They called it the 671. Just another bus engine. What they didn't know was that this bus engine would outlast the tanks it powered, survive direct hits that would destroy conventional power plants, and run for 50,000 hours straight in conditions that killed everything else. This is the story of how General Motors' most boring product became the most feared sound in 3 different wars. To understand why a bus engine ended up dominating battlefields from Korea to Vietnam, we need to travel back to 1938, Detroit. General Motors' diesel division wasn't thinking about war. They were solving a much simpler problem: how to make city buses stop belching black smoke into the faces of waiting passengers. Charles Kettering, GM's research chief, had been obsessed with diesel technology since the early 1930s. But not the massive ship-sized diesels everyone else was building. Kettering wanted something revolutionary, a compact, lightweight diesel that could fit where gasoline engines traditionally lived. The diesel engines of the 1930s were monuments to industrial might. Massive cast-iron blocks, some weighing several tons, designed for ships and stationary power generation. The smallest portable diesel available in 1938 weighed 3,000 pounds and produced maybe 100 horsepower. Kettering looked at these behemoths and saw dinosaurs waiting for extinction. His team at GM Research began with a radical premise. What if they forgot everything anyone knew about diesel design and started from scratch? The answer came from an unexpected source: the two-stroke principle. Now, conventional wisdom said two-stroke engines were for chainsaws and mopeds, not serious power applications. They were dirty, unreliable, and inefficient. But GM's engineers realized that diesel combustion changed everything. In a two-stroke diesel, you could eliminate valves entirely. No valve train, no complex timing mechanisms, just ports in the cylinder walls and a Roots-type supercharger to force air through the system. The design they created broke every rule. Where traditional diesels used 4 strokes to complete a combustion cycle, the GM design did it in 2. Where others relied on natural aspiration, GM forced air through with a gear-driven blower. Where competitors built massive blocks to contain diesel's explosive pressures, GM used a modular design where individual cylinder assemblies could be removed and replaced. The designation 671 was purely functional: 6 cylinders, 71 cubic inches per cylinder, total displacement 426 cubic inches, in a package that weighed just 200 pounds. The first 671 prototype fired up in GM's diesel division facility in December 1937. Engineers expected problems. What they got was 2 to 25 horsepower at 2,100 RPM, running so smooth you could balance a nickel on the valve cover. The secret was the firing order. With a power stroke every 60 degrees of crankshaft rotation, the 671 delivered power so consistently it felt like an electric motor. But here's where it gets interesting. The supercharger wasn't for power. It was for scavenging. Every time a piston uncovered the exhaust ports, the blower would force fresh air through the cylinder, completely purging exhaust gases. This meant complete combustion, minimal smoke, and an engine that could run at full power indefinitely without overheating. By 1939, Detroit city buses were running 671s, and something remarkable was happening. These engines weren't breaking. Where gasoline bus engines needed rebuilds every 40,000 miles, the 671s were hitting 100,000 miles without even requiring valve adjustments, because there were no valves to adjust. Maintenance crews were baffled. Oil changes, filter replacements, and occasional injector cleaning. That was it. The engine's simplicity was its superpower. Then December 7, 1941 happened. Pearl Harbor thrust America into a war it wasn't prepared for, and suddenly every factory in Detroit was converting to military production. The War Department needed tank engines, and they needed them yesterday. The standard tank engine was the Ford GAA, a massive 100 cubic inch V8 that produced 500 horsepower and drank gasoline like a drunk sailor on shore leave. It was powerful, but it had one fatal flaw. It turned Sherman tanks into rolling bombs. One German 80mm shell hitting the engine compartment would ignite the 160 gallons of gasoline, incinerating the crew in seconds. Tank crews called them Ronsons after the cigarette lighter, because they lit first time, every time. Someone at the Ordnance Department remembered those Detroit buses that never seemed to break down. What if they put that boring bus engine in a tank? The proposal was met with skepticism. The 671 made 225 horsepower. A Sherman needed 400 minimum to move its 30-ton bulk at combat speeds. The solution was elegant. If one engine wasn't enough, use two. GM engineers created a transfer case that coupled two 671 engines side by side, their crankshafts synchronized through a common gearbox. The result was the Series 6046, delivering 410 horsepower from 852 cubic inches. But the real advantage wasn't power, it was torque. The twin 671s produced maximum torque at just 1,200 RPM, compared to 2,200 RPM for the Ford V8. This meant better pulling power in mud, sand, and the mountainous terrain of Italy and Korea. The first diesel Shermans, designated M4A2, rolled off Detroit production lines in April 1942. The Army was skeptical. Diesel fuel wasn't part of their standard supply chain, but the Marines, always forced to make do with Army hand-me-downs, saw an opportunity. They were already dealing with diesel fuel for their landing craft. Having tanks that ran on the same fuel simplified logistics immensely. The Marines took every M4A2 they could get their hands on. What they discovered in combat changed everything. Iwo Jima, February 1945. Marine M4A2s are climbing volcanic ash slopes that would bog down gasoline Shermans. The twin 671s, with their massive low-end torque, could crawl up 60-degree grades at idle. Japanese defenders noticed something else. They couldn't hear them coming until it was too late. The diesel's lower frequency exhaust note, around 85 Hz compared to 125 Hz for gasoline engines, dissipated faster in the volcanic soil. By the time Japanese anti-tank crews heard the diesels, the Shermans were already in firing range. But the real test came in Korea, where the engine would face its greatest challenge and prove why Detroit's bus engine was actually a combat genius in disguise. The Korean War started badly for American armor. T-34s provided by the Soviets were cutting through South Korean and early U.S. forces like butter. The T-34's 76mm gun could penetrate a Sherman's frontal armor at 1,000 yards. American 75mm guns bounced off T-34s at 500 yards. It was a disaster. But Marine M4A2s had an unexpected advantage. The diesel exhaust was 400 degrees cooler than gasoline exhaust. In Korean winter conditions where temperatures hit -40 Fahrenheit, this made all the difference. Gasoline Shermans created massive heat plumes visible on Soviet infrared scopes from 2 miles away. The diesels? Nearly invisible until they were within 500 yards. Marine tank crews learned to shut down one engine while idling, running on just a single 671 to further reduce their heat signature. They could creep into ambush positions completely undetected. At the chosen reservoir, November 1950, temperatures dropped to -35. Gasoline Shermans wouldn't start without extensive preheating. Their engines, when they did run, consumed fuel at horrific rates, trying to maintain operating temperature. The M4A2s? The 671s fired up after just 30 seconds of glow plug heating. Diesel fuel doesn't evaporate like gasoline, so it maintains its lubricating properties even in extreme cold. The engines ran smooth at temperatures that seized gasoline power plants solid. Here's something that shocked even GM engineers when they analyzed combat data. The 671 could run with half its cylinders destroyed and keep fighting. The modular design meant each cylinder was essentially independent. One Marine M4A2 in Korea took a direct hit from a Chinese 76 Outsmarted anti-tank gun that destroyed cylinders 2 and 3 on the left engine. The crew simply disconnected the fuel lines to those cylinders and kept fighting on the remaining 10 cylinders. They drove 47 miles back to base under their own power. The mechanical fuel injection system was pure genius in its simplicity. Each cylinder had its own unit injector, a combined pump and nozzle that pressurized fuel to 1,800 psi at the exact moment of injection. No high-pressure lines, no central injection pump, no complex timing chains. If one injector failed, you lost one cylinder, not the entire engine. Compare this to the Ford GAA's carburetor system, which would flood and stall if the tank tilted more than 30 degrees. The 671 would run upside down if you could keep oil pressure to the bearings. Let me paint you a picture of what this meant in combat. Hill 1062, Korea, September 1952. A platoon of Marine M4A2s is holding a ridge against Chinese night infiltration. They've been running their engines for 72 straight hours, providing mobile firepower wherever breakthroughs threaten. The temperature swings from 95 degrees during the day to 25 degrees at night. Any gasoline engine would have destroyed itself from vapor lock, carburetor icing, or simple thermal fatigue. The 671s just kept running. Oil consumption, 1 quart per engine every 12 hours. Fuel consumption, 0.39 pounds per horsepower per hour, exactly what GM's engineers predicted in Detroit. The Chinese learned to fear what they called the growling dragons. The distinctive sound of twin 671s, that deep rhythmic thrum at 850 RPM idle, meant death was prowling in the darkness. Unlike gasoline engines that needed to rev up to operating temperature, the diesels could go from cold start to full combat power in less than 60 seconds. This rapid response capability saved countless infantry units from being overrun. But perhaps the most impressive statistic is this. Of the 1,026 M4A2 Shermans that saw combat in Korea, not a single one was lost due to engine fire after being hit. Every single gasoline Sherman that took a penetrating hit to the engine compartment burned. The diesel fuel in the M4A2s might leak, might even mist, but it wouldn't explode. Crew survival rates in diesel Shermans were 60% higher than gasoline variants when hit by enemy fire. The Roots-type supercharger deserves special attention. This wasn't a turbocharger relying on exhaust gases. It was a positive displacement blower, gear driven directly from the crankshaft at 1.98 times engine speed. 2 3-lobe rotors meshed like gears, trapping air between the lobes and forcing it into the engine. At 2,100 RPM engine speed, the blower was spinning at 4,058 RPM, moving 568 cubic feet of air per minute. This constant mechanically driven airflow meant instant throttle response. No turbo lag, no waiting for boost to build. The moment you pushed the throttle, you had maximum scavenging pressure. The engineering brilliance extended to the cooling system. GM designed a reverse flow cooling circuit where coolant entered at the hottest point, the exhaust ports, and exited at the coolest, the lower block. This prevented hot spots that plagued conventional engines. The cylinder liners were replaceable wet sleeves, sealed with rubber O-rings. If a cylinder was damaged, you could pull the head, extract the liner with a simple puller tool, and slide in a new one. Total repair time, 45 minutes. Try that with a cast-in-place cylinder bore. GM's metallurgy was decades ahead. The crankshaft was forged from SAE 1045 steel, heat-treated to a Brunel hardness of 248-293. This was harder than most tank armor plate. The connecting rods used an I-beam cross-section that provided maximum strength with minimum weight. Each rod could handle 12,000 pounds of force without deformation. The pistons were aluminum alloy with a steel insert for the top ring groove, preventing the ring from pounding out the softer aluminum under diesel's extreme pressures. Now here's where the story takes an unexpected turn. The Soviets, through Lend-Lease, received 402 M4A2 Shermans during World War II. They loved them. Not for their armor or guns, but for those Detroit diesels. Soviet tank crews had extensive experience with diesel engines in their T-34s. But the GM two-strokes were revelation. They ran smoother, lasted longer, and required less maintenance than anything in the Soviet inventory. After the war, Soviet engineers spent years trying to reverse engineer the 671. They never quite succeeded. The precision required in manufacturing the unit injectors, the exact tolerances of the blower rotors, the metallurgy of the valve seats. It was beyond Soviet industrial capability at the time. Captured German reports from the Eastern Front describe an almost superstitious fear of the diesel Shermans. They called them Gespensterpanzer, ghost tanks. They would appear out of nowhere, their low-frequency rumble masked by artillery and gunfire until it was too late. One Wehrmacht anti-tank gunner's memoir describes waiting in ambush for a column of Shermans, clearly audible from over a kilometer away. The gasoline engines announced their approach like trumpets. Then silence. Minutes later, diesel Shermans appeared from a completely different direction. They had heard the gasoline engines too and used them as a diversion. The 671's simplicity made it soldier-proof, and I mean that as a compliment. You couldn't over-rev it. The governor would cut fuel at 2,350 RPM. You couldn't overheat it. The design would tolerate coolant temperatures up to 235 degrees without damage. You couldn't even hydrolock it. If water entered through the intake, it would blow out the exhaust ports before causing serious damage. Marine mechanics in the Pacific reported engines running after being completely submerged during beach landings. Drain the oil, blow out the cylinders, refill, and start. Try that with a gasoline engine. The production story is equally remarkable. GM's Detroit Diesel Engine Division, previously making 50 bus engines per week, scaled to 1,000 military engines per week by 1943. They achieved this without compromising quality. Every single engine was dyno tested for 4 hours before shipping. Power output had to be within 2% of specification. Oil consumption couldn't exceed 1 quart per 12 hours at full power. Any engine failing these standards was torn down and rebuilt. The rejection rate, less than 0.3%. The fuel injection system merits deeper examination. Each unit injector was a masterpiece of precision engineering. The plunger and barrel were matched pairs, lapped together to tolerances of 0.004 inches. That's smaller than a human red blood cell. The injection pressure of 1,800 psi was generated mechanically by a rocker arm driven from the camshaft. No electronics, no sensors, just pure mechanical precision. The spray pattern had to atomize fuel into droplets between 10 and 100 microns, too large and combustion was incomplete, too small and the fuel burned too fast, causing detonation. The genius was in the timing. Injection began at 15 degrees before top dead center and lasted for 23 degrees of crankshaft rotation. This gave the fuel time to mix with the compressed air, reaching an auto-ignition temperature of 1,000 degrees Fahrenheit. The combustion event peaked at 1,900 psi cylinder pressure, but the engine was designed to handle 2,400 psi with a safety factor. This overbuilding is why 671s routinely lasted 500,000 miles in commercial service after the war. Let's talk about field modifications because this is where the 671 really proved its versatility. Marine mechanics in Korea discovered they could increase power by shimming the governor springs, allowing engine speed to reach 2,500 RPM. This produced 270 horsepower per engine, though it shortened engine life to about 1,000 hours. For a tank expecting to survive maybe 100 hours in combat, this was an acceptable trade. They also modified the blower drive ratios. The standard 1.98.1 ratio was conservative. Some units ran 2.251, increasing scavenging pressure from 4 psi to 6 psi. This improved high-altitude performance significantly. In Vietnam, the story continued with M113 armored personnel carriers. These used a naturally aspirated version of the 671 producing 210 horsepower, but Vietnam's combination of heat, humidity, and jungle warfare created new challenges. The engines were running at 95% load capacity, just moving through jungle mud. GM engineers flew to Saigon and created field modification kits. They added aftercoolers to the blower output, dropping air charge temperature by 85 degrees. They revised the cam profiles for earlier exhaust port opening, improving scavenging. They even developed a jungle juice fuel additive that increased cetane rating from 40 to 55, improving cold starting in monsoon conditions. The Viet Cong learned to identify American vehicles by sound. Gasoline engines had a distinctive pitch that carried through jungle canopy. The 671's lower frequency was absorbed by vegetation, making acoustic detection much harder. VC ambush doctrine specified engaging gasoline vehicles first because they burned when hit. Diesel M103s could take multiple RPG hits and keep moving. One famous incident involved an M113 that took 7 RPG hits, lost 3 road wheels, and still managed to extract its infantry squad and limp back to base under its own power. The engine's modularity saved lives. Field repair kits contained complete cylinder assemblies that could be swapped in under combat conditions. A trained crew could replace a damaged cylinder in 30 minutes using basic hand tools. Compare this to the Chrysler A57 multi-bank engine used in some Shermans, 5 separate car engines on a common crankcase. One damaged engine bank meant evacuating the entire tank for depot-level maintenance. The 671 kept vehicles in the fight. Here's a statistic that blew my mind. During the entire Korean War, the mean time between failures for the 671 in combat conditions was 847 hours. The gasoline 4GAA, 296 hours. That's not just reliability, that's the difference between life and death when you're holding a hill against human wave attacks. The 671 didn't just run longer, it degraded more gracefully. As components wore, power would decrease gradually. A gasoline engine would run fine until catastrophic failure. Diesel crews could feel their engines getting tired and request maintenance before breakdowns occurred. The exhaust note itself became a weapon. Tank crews learned to manipulate throttles to create specific sound patterns that mimicked larger formations. 3 tanks could sound like 10 by varying their RPMs in sequence. The Chinese called this ghost multiplication and often reported facing division-strength armor when only a company was present. The psychological warfare aspect was unintentional but effective. Post-war analysis revealed something extraordinary. GM tracked every serialized 671 engine through its military service. Engines built in 1942 were still running in Vietnam in 1969. 27 years of continuous service through 3 wars. Some had been rebuilt multiple times, but the core components, block, crankshaft, camshaft, were original. The youngest Marine mechanic in Vietnam was maintaining engines older than he was. The commercial legacy is equally impressive. After World War II, thousands of surplus 671s flooded the civilian market. They powered everything from fishing boats to generators to oil rigs. The Detroit bus fleet that started it all? Some of those original 1939 buses ran until 1987. Nearly 50 years of daily service in stop-and-go city traffic. The engines outlasted 4 chassis rebuilds. When finally retired, compression tests showed they were still within 10% of factory specifications. The 671 influenced diesel design worldwide. The principle of unit injection was copied by everyone from Cummins to Caterpillar. The two-stroke diesel concept evolved into EMD locomotive engines, some producing 6,000 horsepower from the same basic architecture. Even today, you can buy brand-new 671 engines. MTU Detroit Diesel still manufactures them for marine and industrial applications. The design is essentially unchanged from 1938. Why mess with perfection? Let's address the elephant in the room. Why didn't the U.S. Army embrace diesel Shermans? Politics and logistics. The Army had invested heavily in gasoline infrastructure. Every depot, every fuel truck, every supply chain was built around gasoline. Switching to diesel would have required reorganizing the entire logistics network during wartime. The Marines, operating independently with the Navy, had flexibility the Army didn't. They could specify their own equipment and fuel requirements. This bureaucratic accident saved thousands of Marine lives. The Soviets had no such constraints. They standardized on diesel before the war and never looked back. They produced over 57,000 T-34s, all diesel-powered. When they received American diesel Shermans through Lend-Lease, integration was seamless. Soviet commanders specifically requested M4A2s over gasoline variants. They valued reliability over maximum power. A running tank with 400 horsepower beats a broken tank with 500 horsepower every time. Modern tank designers still study the 671. The principle of modular construction appears in everything from the German MTU MB 873 to the Ukrainian 6TD. The idea that battlefield damage shouldn't mean complete engine replacement was revolutionary in 1942. Today, it's standard doctrine. The M1 Abrams AGT 1500 turbine was chosen partially because it can run on any fuel, including diesel. The lesson of fuel flexibility learned in Korea wasn't forgotten. But here's the real kicker. The total development cost for the 671, adjusted for inflation, was $48 million. The engine family generated over $2 billion in revenue for GM through 1990. It powered the arsenal of democracy, saved countless lives, and revolutionized diesel technology, all from a bus engine that nobody wanted. The engineers who designed it were thinking about reducing smoke at bus stops. They accidentally created one of the most successful military power plants in history. Charles Kettering died in 1958, living just long enough to see his lightweight diesel prove itself in Korea. His obituary barely mentioned the military applications. He was remembered for automotive innovations and industrial research. But every Marine who made it home from Iwo Jima, every tanker who survived Korea, every M113 crew that lived through a Viet Cong ambush owes their lives partly to Kettering's obsession with making a better bus engine. Today, when you hear military analysts debate electric versus hybrid versus conventional powertrains for future combat vehicles, remember the 671. The best military engine isn't always the most powerful, the most advanced, or the most expensive. Sometimes it's the simplest, most reliable, most maintainable design that wins wars. The 671 wasn't trying to be a combat engine, it was just trying to be a good engine. That's what made it great. The last M4A2 Sherman was retired from military service in Paraguay in 2018. It had been upgraded with modern optics and communications, but the power plant was original. 2 671 engines manufactured in Detroit in 1944, still running 74 years later. The tank is now in a museum, but the engines still start. Visitors are amazed by the smooth idle, the lack of smoke, the mechanical symphony of precision engineering. They expect something exotic, something high-tech. What they get is the sound of Detroit practicality, engineered simplicity that conquered the world one bus stop at a time. So next time you see a city bus, remember that its ancestor saved democracy. The 671 proved that innovation doesn't always mean complexity. Sometimes the most revolutionary act is making something simple work reliably under impossible conditions. The Soviets had bigger diesels. The Germans had more sophisticated ones. But only America put a bus engine in a tank and made it work. That's engineering. That's innovation. That's the Detroit diesel that outsmarted every tank in Korea, one reliable revolution at a time. What's your take on this incredible story? Have you ever encountered one of these legendary engines? Drop a comment below and share your experience with Detroit diesel history. And if you want more stories about unlikely engineering heroes that changed warfare, make sure to hit that subscribe button. Until next time, keep those engines running, and remember, sometimes the most boring solution is the one that wins wars.